Hi, my name is Harish, and I'll be talking about our work on using the computer graphics pipeline for relational query processing. There has been a lot of recent work on using GPUs in databases, especially in academic research, ranging from designing custom operators such as joins and group bys to designing techniques for data placement and even building entire GPU-based database systems. This is in part because GPU technology has improved by leaps and bounds in the last few years, and we are seeing generational performance improvements that was not seen before. The CPU GPU memory bottleneck is also rapidly decreasing with newer technologies such as PCIe 5, NVIDIA's NVLink, and AMD's Infinity Fabric. We therefore believe that this is the right time to revisit the way GPUs are used in databases. So why did I say revisit when there are already many proposals using GPUs in databases? The conventional wisdom in all the current approaches is to use the GPU simply as a set of parallel processing units. Our goal in this work is instead to go back to the basics. We want to use a GPU for what it is designed for. And it is designed to draw complex 3D scenes at high frame rates. Current generation GPUs can render scenes with millions of points as fast as 120 FPS, sometimes even as high as 240 FPS, which is a standard for competitive gaming. This kind of high frame rate is accomplished through what is called the graphics pipeline. The graphics pipeline basically splits the drawing process into a sequence of stages, a subset of which are programmable. So let's first look at how a simplified graphics pipeline works. Consider a set of vertices that makes up the mesh to be rendered. It first passes through what is called the vertex shader, which transforms the points to the position relative to the camera. The logic in this stage is programmed by the developer. The transformed mesh is then passed through the vertex post-processing step, which performs operations such as rasterization and clipping and generates a set of fragments. A fragment can be thought of as data corresponding to a pixel in the end image. These fragments then pass through the fragment shader, where the developer can add the necessary lighting, shadow information, and assign a color to each fragment. The colored fragments then go through a fragment processing stage, which combines them after performing operations such as blending and depth culling to generate the final rendered image. There are several advantages to using this graphics pipeline since the hardware is optimized to perform these tasks efficiently. Mainly, the fixed functions of the pipeline is implemented in hardware. This is a primary task of a GPU, and the drivers play a key role in optimizing the operations depending on the hardware. It also performs any memory prefetching, caching as necessary, and appropriately schedules the parallel threads. In a sense, the developer can expect automatically tuned performance and need not consider low-level details of the hardware. Furthermore, the graphics pipeline is supported on all GPU hardware and is therefore portable across hardware vendors. While this is all great, especially in a graphics setting, can it be used in a database setting? To test this, we tried to design two heavily used database operators, namely the equijoin and groupby, using the graphics pipeline. Let's first look at the equijoin operation. There has been lots of prior work showing that GPUs help speed up the join operation. In this work, we specifically focus on the hash join operation, which takes as input integer columns of two tables R and S, builds a hash table on the join attribute of R, and probes tuples in S against the hash table built on R. Let's now look at how the build phase can be composed using the graphics pipeline. We will treat the join attribute of R as a set of vertices. We will then transform these vertices into vertex shader using the hash function. In this case, the hash function maps the attribute values to two-dimensional points. The fragments that are generated are then passed through the fragment shader, where appropriate colors are assigned to these fragments. In our context, colors are used to denote the hash table entries. The different fragments are then combined together to form a hash image. Note that to handle duplicates or hash collisions, we make use of a stack of images which together form the hash table. You can find the detailed algorithm in the paper. So what advantages do the above approach provide us with? First, consider questions such as what memory to use, how to lay out the data across memory, what is an efficient way to prefetch data into local memory. We need not bother about any of these questions. We simply bind R as a vertex buffer, and the driver automatically takes care of all of these questions. Similarly, we simply have to say draw n vertices, and the driver will decide how many threads and thread groups to spawn, and also schedule the threads across vertex and fragment shader instances to best utilize the GPU. Even the write to output images is done in a lazy fashion, thus giving the driver the flexibility to schedule the I/O. The probe is accomplished in a similar fashion. The join attributes of S is bound as a vertex buffer. Additionally, the hash stack is bound as a texture, thus allowing the use of efficient texture lookups. The vertex shader then applies the hash function of S and tests for a match with the hash table. A vertices not matched gets clipped by the vertex post-processing step. The fragment shader then assigns the output pairs as colors to the generated fragments, which are finally collected together to obtain the join output. There are, of course, several challenges when implementing our approach. First, what about data that does not fit in GPU? For this, we choose the same tactic that is common in the literature, that is to perform a partition hash join. For this work, we chose to partition on the CPU. However, note that one could also partition using the GPU, similar to Triton join, if the hardware supports it. Second, to reduce the time spent on CPU-GPU transfers, we pipeline partition copying and compute. Third, skewed data can also result in too many hash images, which can adversely affect the performance. To overcome this, we introduce a runtime statistics computation step, which chooses a build table dynamically based on the number of hash images that is required. In case this number is still too large, we optionally flatten the images. You can find the performance numbers for such scenarios in the paper. Let us now briefly look at the group by operation. The first step of the group by is similar to that of the join. We basically compute the hash table, with the only difference being that we ignore duplicates during the computation. The aggregation step is then accomplished using the graphics pipeline as follows. Here, the group by column and values are again bound as vertex buffers, and the hash table bound as textures. The vertex shader is then used to identify the unique output locations for each tuple, and the corresponding fragments are generated. The value to be aggregated is then assigned in the fragment shader. What is different in this pipeline compared to the join pipeline is that we make use of the inbuilt blending functionality to compute the aggregation. This allows us to support count, sum, average, minimum, and maximum as aggregate functions. The hardware then performs this blend and generates the required output. While this algorithm illustrates the case of a single attribute group by, we have also extended this approach to support multi-attribute group bys. We implemented our approach using the Class platform, Vulkan API, and C++ as part of a system called Garuda. Our current implementation assumes that the data fits in CPU memory. We evaluate our approach on a vanilla desktop with a PCIe 4 interface and an NVIDIA RTX 3080 GPU. In this talk, I will present results involving data from TPCH tables. Let's first look at the join operation. We execute 4 join operations between the different TPCH tables. For this experiment, we use a TPCH data with a scale factor of 1000 or 1 terabyte. We compare our approach with the state-of-the-art hardware-conscious join that was implemented using CUDA. Note that our approach, Garuda, outperforms the hardware-conscious join by at least a factor of 2. To test the group by performance, we pre-materialize the join between the line item and orders tables and perform three different group by operations resulting in different number of groups. To compare, we use the OpenCL based implementation which we call TGB. Further, we perform an exhaustive search to identify the best parameter setting for TGB. Note that even when using the best setting for TGB, Garuda still performs better than TGB. To test the portability of our approach with conventional GP-GPU methods, we also tested our group by implementation against TGB on a laptop with Intel graphics processor. We use the TPCH 100 GB data for this experiment. We ran the same group by queries as before and again performed an exhaustive search to identify the best parameter setting. To show the dependence of the parameter setting on the hardware, we also use the parameters identified in the previous desktop configuration. Note that when running TGB using the desktop parameters, one of the queries crashed, while the other two queries ran slower compared to using the most suitable parameters. Our approach, on the other hand, performs on par or better even against TGB with the best parameter setting. To conclude, graphics performance has seen incredible improvements in recent years, but surprisingly not being taken advantage of outside of the graphics domain. Compared to conventional GP-GPU approaches, using the graphics pipeline provides automatically tuned performance as well as portability across hardware. We therefore believe that this is a promising way to extract the full power of the GPU. There are, however, several interesting challenges that still need to be tackled, such as are there other operators that can also benefit using the graphics paradigm, and how all of this is going to fit in a commercial strength database engine. The latter is an important question since, in spite of all the research happening in the space, it has been hard for GPUs to gain traction with the major database vendors. With this, let me conclude this talk. Thanks for listening.